Welcome to this new inside code video where we will see the breadth first search algorithm. In the last video, we've seen the depth first search algorithm, which is an algorithm that traverses a tree or graph by going deep into the first path, then backtracking, then going deep into the second path, and so on. Click on the little eye at the top right of the screen to watch the video if you didn't watch it yet. But in this video, we will see the breadth first search algorithm, which also traverses a tree or a graph, but in another way that I will introduce now. Okay, let's suppose that you own a company that is represented by this tree, where the relation between nodes means that the parent node is a manager of the child node. And now you want to iterate over your employees in a hierarchical way. In other words, this level, which is you, then this level, and so on. By doing so, you'd have done a breadth first search traversal, because traversing a tree in breadth first search means to traverse it level by level, and it's exactly what you did here. Now an example with a graph. If you've already been on LinkedIn, you probably noticed the first, second, or third notation after someone's name. But do you know what does that mean? In reality, it represents the connection degree with that person. If you are directly connected with the person, then the connection degree is 1. This is why you see written first next to it. If you aren't directly connected but you are connected to one of his connections, then the connection degree is 2. Second. If you are connected to someone that is connected to one of his connections, then it's 3, third, and so on. You got the concept. So if we have a graph of LinkedIn members and their connections, to calculate the connection degree between two people, we start from person A, we check its connections. If we don't find B, then we check connections of connections, and so on until we find B. Here it's a 4-degree connection. And by doing so, we'd have done a breadth first search traversal of the graph, by starting from person A. So in brief, breadth first search traversal is just traversing the tree or the graph by layers, or levels. We start at a certain node, it represents the first layer, then we traverse its neighbors, they represent the second layer, then neighbors of neighbors, they represent the third layer, and so on until there are no remaining unvisited nodes. Okay, but how does the algorithm work? To know it, let's take a Goulot tree. In breadth first search traversal, we want to visit this node, then this node, then this node, then this node. And now we want to go to this one, but the problem is that there is no edge between them, so we cannot directly jump. This is why we have to find another way to go to the next node. You can see that the only way to go there is when we are on the yellow node, because it's the only one that has a link with it, so we have to find a way to kinda stall the node so that we don't lose the path. And the best way to do that is to use a queue. I know that it seems messy and complicated like this, but the process is really smooth and understandable. You'll see it with this example. We have this tree and we want to traverse it in breadth first search, and here is the queue that we're gonna use. It initially contains the root. What we're gonna do is that while the queue still has elements, with the queue we print the value and we enqueue the children to not lose access to them. Let's start. With the queue we print the value and we enqueue children. The queue still has elements, so we continue. With the queue, we print, and we enqueue children. Again, with the queue, and you can see that we move to the second element of the same level instead of going deep like for depth first search. We print, and this node doesn't have children, so we have nothing to enqueue. Next node, with the queue, we print, and we enqueue children. Again here, with the queue, and you can see that we could now visit the first node of the third level after finishing the second one. It's because when inserting the node whose value is 12, we inserted it at the bottom so that we could finish traversing nodes of the same level before moving to it. It's the main idea of enqueuing, and this is why I told you that the queue is the best way for this kind of process. Now we print and it has no children, so we just continue. With the queue again, we print and we enqueue children. And this process gets repeated until there are no elements left in the queue. For the code, we create a function that takes the root of the tree as parameter, we directly exit if the tree is empty, then we need to create a queue that initially contains the root, but we can just use an array. Now while the queue isn't empty, we dequeue the next node by popping the first element from the array, we print its value, and we iterate over its children to enqueue them. That's it. But a little problem here is that popping the first element from an array costs O of n, because all remaining elements must be moved back by one cell, So instead of doing that, we put an index I initialized to 0 that represents the index of the next element of the queue to be visited, and that we increment after each dequeuing. All that while I is smaller than the length of the queue, because when I reaches the length of the queue, it means that we finished traversing all the elements. Here is the full code. You can pause the video, but know that you'll find it in the description. Now we've seen how to apply breadth first search algorithm on a tree, but is it the same logic for graphs? The answer is yes, but we have to add a set of enqueued nodes to avoid enqueuing the same node twice. But before jumping to the code, let's traverse this graph in breadth first search to see how it works. Let's start from node 0, so we need the queue that initially contains it. We dequeue, we print, and we can enqueue both 1 and 3 because they are not enqueued yet. We continue, we dequeue 1, we print, and 0 and 3 are already enqueued, but 6, 8, and 5 are not, so we enqueue them. Now we dequeue 3, we print, and we can enqueue 2 and 4. Now we finish traversing the second level and we move to the third one that starts with the node 6. We dequeue, we print, and we can enqueue 7 only. Remember that we can enqueue only neighbors that are not enqueued yet. Now we dequeue 8, we print, and we can enqueue 10 only. And this process gets repeated until the queue becomes empty, like for trees. Now for the code, it's quite the same as the one for trees, we just have to add a few things. The function here takes 2 parameters and not only one, because we need the graph and the node from where we start. Then we need the queue, but we also need a set of enqueued nodes that initially contains the root. Then everything remains the same except for the loop where we have to check that a neighbor isn't enqueued yet before enqueuing it. And we also have to add it to the set of enqueued nodes after the enqueuing. That's it. Note that in this code, the graph is represented by an adjacency list, like this one. Now that you know how both DFS and BFS work, we can jump to the question, which one is better? In reality, none of them is better than the other. They are both useful, it just depends on the situation. For example, if you know that the element you're searching for is probably close to the initial node, then it's better to use breadth first search, because it starts by checking close nodes then moves to those further. Else if you know that the element you're searching for is probably far from the initial node this time, then depth first search is better, because it starts reaching deep nodes before BFS, so it will take less time to find your target. All that because breadth first search has to traverse all close levels before reaching deep ones. We can find more examples like this. For example, if we're playing a 2-player game and want to get all possibilities, it's more appropriate to use depth first search, because you want to know what happens when you play your turn, then the other player plays his turn, then you play your turn, and so on until arriving at the end of that scenario. Then you move to other ones. Else if you want, for example, to get the shortest path between 2 nodes in an unweighted graph, as we did with the connection degree example, then breadth first search is more appropriate, because as said earlier, it starts by checking close nodes than those further. So it's guaranteed that when you find the searched node, you'd have passed from the shortest path. This is not the case with depth first search, because even if you can find the searched node, but it doesn't necessarily mean that you took the shortest path, like the example on the screen. And the cool thing with DFS and BFS is that they can be used in problems where there is neither tree nor graph, because as you may know, almost every problem can be represented with a graph. An interesting example is the word ladder problem. We have a begin word, an end word, a word list, and our goal is to find the length of the shortest possible transformation sequence to go from begin word to end word, knowing that the transformation means to change only one letter and the new word must be in word list. Even if no graph had been mentioned in the problem, but we can represent those words as nodes of a graph, and if there is an edge between 2 nodes, it means that we can do a transformation. In other words, they differ by 1 letter only, like with the words hot and dot. Now that we have the graph, we just apply a breadth first search starting from begin word and we search for end word. Finding it will give us the length of the shortest transformation sequence. You want to know the algorithm for this problem, then have a look at the course in the description. It's a course where you will find this problem alongside 49 other ones. I really recommend you to enroll if you want to become better in solving coding problems, in algorithms, in data structures, and in time and space complexity analysis. So it will sharpen your skills and it will also support the channel, which is pretty cool. Now we arrived at the end of the video. In BRIEF, DFS and BFS are two algorithms used to traverse trees and graphs in different ways, and they are both useful and interesting to know. You just need to know when to use one over the other. I hope that you enjoyed this video. Please leave a like and subscribe to the channel. Give me your feedback in comments. Don't forget to have a look at the course, and see you in the next video.